2,4,6-trinitrotoluene, more commonly referred to as TNT, is an aromatic compound that has three nitro groups attached to the 2,4,6 positions on toluene or methylbenzene. It was first prepared by German chemist Julius Wilbrand in 1863, who wanted to create a yellow dye. Its explosive capabilities were not known at the time since there was not a strong enough detonator to cause an explosion. In 1870, chemists Friedrich Bilstein and A. Kohlberg managed to produce 2,4,5-trinitrotoluene, which is an isomer to 2,4,6-trinitrotoluene. This was then followed by Paul Hepp, who prepared pure 2,4,6-trinitrotoluene in 1880. Even then, its explosive properties had not been well investigated at the time. Explosive properties of TNT were first discovered by another German chemist named Karl Hausermann in 1891. Later in history, TNT would prove itself as a superior explosive on the battlefront. The German armed forces used TNT as a filling for artillery shells in 1902, and it was a much more formidable weapon given the fact that, unlike leaded-filled shells of the British, the TNT shells exploded only after penetrating armor, not on impact, which meant more damage dealt. TNT was also more valued due to its stability to shock and friction. Compared to nitroglycerin, there was a much lower chance of accidental detonation with TNT. Since TNT has a melting point of around 80 degrees Celsius, a temperature far below any risk of spontaneous combustion, TNT was able to be safely poured in molten form or mixed with other explosives, proving its versatility. One problem that did arise in the usage of TNT in World War I was its toxicity. During World War I, exposed workers suffered from liver abnormalities, anemia, and other red blood cell damage and respiratory complications. Trinitrotoluene is easily absorbed through direct contact or airborne dust and vapor, potentially causing dermatitis, eczema, and yellow stains in the nails, skin, and hair. Applications of TNT have not changed much from the past. Its main usage still remains as an explosive. It is, however, more commonly used as an explosive in construction due to its low sensitivity, making it a safer explosive. And while it is still used as an explosive in warfare, it is now more often mixed in with other explosive compounds. These blends are called synergistic explosive blends, comprising a variable percentage of TNT plus other ingredients. Examples of blends containing TNT include Amtex, Amitol, Amonol, Baritol, Ednitol, Octol, and Tritonol. TNT just barely dissolves in water or absorbs it, which allows it to be effectively used in wet environments. To detonate, TNT must be triggered by a pressure wave from a starter explosive called an explosive booster. TNT has the chemical formula C7H5N3O6 and a molar mass of 227.13 grams per mole. It is a symmetrical molecule. Now, with a few simple concepts of the molecule tucked away, I can take a deeper look at the molecule. First, we will look at all of its functional groups. Attached to the benzene ring are three nitro functional groups and one methyl group. The nitro groups form nitro compounds, organic compounds that contain one or more nitro NO2 functional groups. The nitro group is an explosive 4, a subgroup of functional groups that give organic compounds explosive properties. The nitro group is also strongly electron withdrawing. Because of this property, adjacent CH bonds to the nitro group can be acidic. For similar reasons, the presence of nitro groups in aromatic compounds retards electrophilic aromatic substitution but facilitates nucleophilic aromatic substitution. Nitro groups are polar and soluble in water. Since there are three nitro groups, it makes the otherwise nonpolar benzene and methyl slightly polar. We will talk about how to add a nitro group to an organic compound in the section where we synthesize TNT. The other functional group that is present is the methyl group. The methyl group is an alkyl group derived from methane that contains one carbon and is bonded to three other hydrogens, CH3. Methyl groups are nonpolar and insoluble in water. Now we can talk about the reactions that this organic compound will undergo. Because the primary component of trinitrotoluene is a benzene ring, as an arene, the benzene ring will only undergo substitution reactions. This type of aromatic electrophilic substitution of the ring will take place during the synthesis of TNT in the form of multiple nitrations that occur as a part of the synthesis. Therefore, aromatic electrophilic substitution will be discussed in the synthesis portion. Another reaction that the TNT might undergo is free radical substitution, as indicated by the methyl group. The final reaction I will bring up is a reaction that occurs when a nitro group is reduced into an amine. Free radical substitution begins with the homolytic fission of a diatomic halogen under UV light. This forms halogen free radicals. This is the initiation step. Free radicals are a species with an unpaired electron. Free radicals are very reactive because of this unpaired electron. The next step is the propagation step. The halogen free radical is very reactive, and when it collides with our TNT, or more specifically the methyl group, the free radical will take a hydrogen from the methyl group, forming a hydrogen halide and a radical methyl group. The radical methyl may react with a diatomic halogen, which then creates a halogen radical, hence the propagation. The final step is termination, where in the creation of a radical methyl, another radical halogen will attach itself to it. Thus, the final products are a hydrogen halide and a halogenoalkane in the form of a halogen attached to the methyl group of TNT. However, this is essentially what free radical substitution would be for methylbenzene, hence the diagram. We also had chlorine as our diatomic halogen. The reduction of nitric compounds are chemical reactions of wide interest in the organic chemistry. The conversion can be affected by many reagents. This reduction happens when a nitric group is reduced into an amino group, NH2. Let's take a look at when nitrobenzene is reduced to aniline. Note that nitrobenzene will be an example of what happens when one of the three nitric groups on TNT are reduced. There are hundreds of ways for this process to occur, with hundreds of reagents, and the overall reaction looks like this. The reduction of nitroaromatics is conducted on an industrial scale. Many methods exist, such as catalytic hydrogenation using Raney nickel or palladium on carbon, platinum for oxide, or nickel. You can also use hydroiodic acid, samarium, titanium 3 chloride, tin 2 chloride. It's just a lot of ways to do it. Now we can talk about the structure and hybridization. All carbons in the aromatic ring are sp2 hybridized, and the bond angles are 120 degrees. The carbon in the methyl group are sp3 hybridized, so its bond angles are 109.5 degrees. Nitrogen is also sp2 hybridized and has a 120 degree bond angle. There are 21 sigma bonds and 6 pi bonds. The bond lengths between the delocalized pi bonds in the benzene is about 0.140 nanometers. The NO bonds have a length of around 125 nanometers. The nitrogen groups are attached to the benzene ring and are trigonal planar structures. The methyl is in a tetrahedral structure. With 3 NO2 groups and a CH3 group, there will be a net dipole moment. Therefore, dipole-dipole interactions and van der Waals interactions are the ones that are present in this molecule. Now we can take a look at bond energies, combustion, and its explosive property. The complete combustion reaction for 1 mole of trinitrotoluene is as shown. And now we know you can look up the bond enthalpies online, but with the following information, we can calculate the enthalpy change of combustion. The ones in red are the bonds broken, the ones on the reactant side, and the ones in blue are the bonds formed, the ones on the product side. Now, to calculate the enthalpy of combustion, we simply subtract the bonds broken by the bonds formed enthalpy, which then yields around negative 5,863.5 kilojoules per mole as the combustion enthalpy. Now, a combustion reaction is different from an explosion reaction. In the combustion reaction, the oxygen comes from an external source, air. In the explosion, the oxygen is contained in the explosive material. So what makes TNT explosive? As mentioned before, it is due to the presence of an explosive-phore, the nitro group. Explosive-phores are functional groups in organic chemistry that give organic compounds explosive properties. Nitrogen-containing explosive-phores are particularly strong because, in addition to providing oxygen, they react to form molecular nitrogen, which is a very stable molecule, N2, and thus the overall reaction is strongly exothermic. The gas formed also expands, causing the shock wave, which is observed when TNT is exploded. TNT is composed of elements carbon, oxygen, and nitrogen. And when TNT explodes, it forms several covalent gases involving CO, CO2, and N2, which are very stable, which again, the production of these is very low energy, stable bonds. That means a great deal of energy is released. It should be noted that most explosives contain these same elements. The three fairly large nitro groups bound to toluene cause strain on the structure of toluene. Remember that groups of electrons repulse each other, so that's important. The other compounds under similar conformational strain are also explosive for this same reason. Now we can get around to talking about how to synthesize trinitrotoluene. The main ingredient in TNT is, as mentioned before, methylbenzene or toluene. Toluene is colorless and flammable and has a benzene odor. Has a boiling point of 110 degrees Celsius, a melting point of negative 95 degrees Celsius. In general, it is a stable compound, but it will react with nitrogen oxides or halogens, which is the property we want. This essentially tells us that it is more reactive than benzene towards electrophiles. Toluene was first isolated in 1837 by Philippe Walter when he was distilling pine oil. While toluene is in general isn't mass produced through the process of distilling pine oil, it is still produced during petroleum refining operations, and it is a direct byproduct of styrene production, and it is indirectly created as a byproduct of coke oven operations. Coke being a term used for a byproduct of burning coal that burns hotter and cleaner than it. However, the main method that it is produced is in the laboratory. In theory, there are many ways for toluene to be made in the lab, but one of the relatively inexpensive ways of producing toluene is through this reaction. So as you can see in the picture, the reaction consists of benzene in liquid form added with chloromethane in the presence of a Lewis acid, in our case aluminum chloride, and heat is required as well. In this process, we obtain products toluene in liquid form and hydrogen chloride in the form of gas. While we won't go into deep detail on how the reaction to form toluene happens, since it's not the compound to be analyzed, this is how the main ingredient in TNT, toluene, is formed. Once we've obtained the essential toluene, the next main step is to put toluene under the process of nitration. More specifically, this type of reaction is called electrophilic aromatic substitution, since we are essentially going to be substituting a hydrogen from an aromatic compound, in our case toluene, with a nitronium ion. For our specific reaction, we will have toluene undergoing this process of electrophilic substitution around 3 times. The overall reaction will essentially be toluene added to nitric acid in the presence of heat and a catalyst of sulfuric acid. The only reason we need this catalyst is to produce our electrophile. Also recall that in a reaction, a catalyst will not be used up. The first step in this process usually is the creation of the electrophile, and in our case, the nitronium ion. Here's a picture of the process of creating the electrophile. As observed, you can see that the nitric acid are reacting with the catalyst, sulfuric acid. The central nitrogen in the nitric acid has a formal positive charge. Now, the purpose of the sulfuric acid is to help the nitric acid generate the electrophile. The OH on the nitric acid is a bad leaving group. Through a process of protonation, the hydrogen on the sulfuric acid will leave to connect with the OH on the nitric acid. This creates a much better leaving group of H2O, which then disconnects from the complex, leaving an electrophilic nitronium ion and water. The next step is for the nitronium ion to be substituted into our toluene, and this is what the process looks like. So while we did produce the nitronium ion, there is no space for it on toluene, so the first step was to remove a hydrogen and make space. Recall that in the creation of the nitronium ion, we created a negatively charged hydrogen sulfate ion as a result of protonation. This anion is happy to take hydrogen from toluene, which can now create a bond with the nitronium ion. However, we aren't done yet. What we created in these steps was only mononitrotoluene. In order to manufacture proper TNT, labs will continue this process of nitration 3 times to gain 2,4,6-trinitrotoluene. Preceding each phase of nitration, the temperature will have to be increased for each reaction to occur. After the first nitration, we go mononitrotoluene. After the second, we get dinitrotoluene, and after the third, we finally get our trinitrotoluene. There are also many other products that do come up as a result of the reaction, like other asymmetric unstable isomers of TNT, and other oxidized products, and so on. Manufacturers will limit the amount of undesired products by performing the third nitration in a solvent called oleum, which is used as a catalyst. Oleum is a mixture of sulfuric acid and disulfuric acid. The mechanism for the third nitration is essentially the same, but with less water. Then manufacturers will wash TNT or whatever final solution they come up with in a bath of other chemicals to finally isolate the symmetric 2,4,6 trinitrotoluene.